Welcome back everyone. In this lecture I will continue to actually talk about the properties of the roots. So, let us fix again some notations as before. So, we take G to be finite dimensional semi simple Lie algebra and H is being a maximal toral subalgebra of G. So, then we have this root space decomposition G equal to H direct sum G alpha, alpha coming from phi. So, where this G alpha are the simultaneous eigenspaces. So, those x in G such that the bracket H x is given to be alpha of H x for all H in H. So, we observed many things about these root spaces. So, for example, we proved that the span of phi is exactly equal to H star and 0 is not in phi, and if alpha is in phi, so then we observe that minus alpha is also in phi, and if alpha is in phi and C alpha is also in phi for some C non-zero. So, then we observe that C must be plus or minus 1. So, note that for alpha beta is in phi. So, we also observe that this particular type of roots beta minus beta of H alpha alpha, this also must be a root, and this is something we proved using SL2 representation theory. So, now what we will do, we will actually so we are working over this H star. So, which is the span of phi over complex numbers. So, somehow we want to bring down this ground field to real numbers, so that we can use some ideas from Euclidean geometry. So, for that purpose we need to actually see how one can actually bring down this complex numbers to real numbers. So, in order to do that, so we also proved this following, we will use this fact. So, beta of H alpha is actually integer for all alpha beta is in phi. So, this is the fact that will be used in order to bring our ground field to real numbers. So, let us see how one does this. So, for that purpose let us recall what we have done so far. So, we have identified this H with H star via the killing form. So, this is something very important, we will use it again and again. So, this identification if you recall, so how we did it. So, we have this H to H star, the map H goes to kappa of H comma dash. So, this map we actually proved it is an isomorphism, and given pi we associated the pre-image to be T pi. So, in particularly the T pi is uniquely defined using the following equation, the kappa of T pi comma x is equal to pi of x for all x in H. So, this is how T pi is defined. So, now what we do, we take the killing form that is defined on H star and then pull it back to H. Oh sorry, the killing form is defined on H. So, we will actually push it to H star. So, how we do, again we have this identification of H with H star using the killing form. So, now just use that identification. In particularly pi goes to T pi. So, that is the map we are going to use. So, what we do, we just define this inner product or the bilinear form gamma delta to be kappa of T gamma T delta for all gamma delta coming from H star. Okay. So, now it is immediate that this form that we have defined is symmetric non-degenerate bilinear form on H star. So, that because it will have all the properties that the killing form that has on H. Okay. So, now what we will do, since this span of phi is H star, we will actually fix some bunch of roots that is the basis of H star. Okay. So, span of phi over C is actually H star. So, in particularly there exists a basis alpha 1 etcetera, let us say alpha L inside your phi. So, this is the basis of H star. So, we fix this basis and work with this basis. So, given beta inside phi, so we will write this beta as sum of C I alpha I, where I range from 1 to n. So, now a priori the C I, they are all coming from complex numbers. So, these are all coming from complex numbers. So, what we claim now? So, we claim that these C I's indeed they come from rationals for all 1 to n. Okay. So, this is again immediate corollary of beta of H alpha being integers. So, let us do this. So, we take this equation beta equal to summation C I alpha I range from 1 to L. So, then we compute this twice beta of alpha j divided by alpha j alpha j. So, then you can see that if you replace beta by the summation C I alpha I and then use the linearity in the first variable of this form, then you get this is exactly equal to summation I range from 1 to L C I twice alpha I comma alpha j divided by alpha j alpha j. So, this is what we get. So, note that this beta of H alpha. So, this is nothing but twice beta of T alpha divided by kappa of T alpha comma T alpha. So, this is by definition twice kappa of T beta comma T alpha divided by kappa of T alpha comma T alpha. So, now if you identify the inner product gamma delta by this kappa of T gamma T delta. So, then you can see that, so this forces that beta of H alpha is nothing but twice beta alpha divided by alpha alpha. We know that these are all integers, okay, for all alpha beta inside phi. So, this is what we are going to use. So, in particularly this particular equation. So, if you treat Ci's as unknowns, so then all these numbers that are appearing here 2 beta alpha j divided by alpha j and then these numbers twice alpha I alpha j divided by alpha j they are all integers. So, this star can be treated as actually system of L equations with L unknowns over integers. So, this is just immediate from beta of H alpha being integers. Okay. So, this star you can treat it like, so this is a system of L equations with L unknowns. So, again it is happening over integers. In particularly, so because to solve system of equations one has to go to the field. So, the smallest field that contains Z will be Q. So, this is happening over Q. Now, note that this alpha 1 etcetera alpha L, that is the basis of H star. So, this inner product the bilinear form that we have defined. So, that is actually non-degenerate on H star. So, that forces that if we take this matrix alpha I alpha j, where 1 less than or equal to I, j less than or equal to L. So, this L by L matrix. So, this L by L matrix, so this must be invertible. So, now if this is invertible and then if you multiply each column by or row by some non-zero scalar, that also must be invertible. So, then that would imply that this new matrix which is twice alpha I comma alpha j divided by alpha j comma alpha j. So, this matrix, this is also L by L matrix. So, this is also invertible. So, this is also L by L invertible matrix. So, since this is actually invertible matrix and all these entries are, these are all integers. So, that means the inverse of this matrix one can obtain over rationals. Okay. So, since this system of equation is actually defined over integers and even the matrix that is involved actually has inverse inside rationals. So, that forces that the CIs must be rationals. Okay. So, this immediately proves that CIs are all rational for all I range from 1 to L. So, now indeed what we have proved, given any beta, we proved that beta must be inside span of this phi over q. Okay. So, that means if we denote EQ by span of this phi over q. So, then you can see that this EQ is also same as span of this alpha 1 etcetera alpha L over q. Okay. So, this is very important q subspace of our H star. Okay. Of course, to get real vector space, what we do, we just tensor over real. Okay. So, to get this real space which we denote it by E. So, this is the real space. So, what we do, we just take EQ and then tensor over real and then over Q. So, this is how we are going to extend the scalars from Q to R. But before that, let us understand what happens to the bilinear form when we actually restrict to this EQ. Okay. So, that is going to help us to understand how the bilinear form will behave on E. Okay. So, note that if we take this lambda and mu from H star, so then we can compute the bilinear form very explicitly. So, the bilinear form is given by kappa of T lambda comma T mu. But note that this T lambda, so this is actually add semisimple element. So, this is add semisimple element and how it acts. So, T lambda acts on H as 0 and then it acts on x alpha as just alpha of T alpha times x alpha, and this is true for all x alpha inside G alpha. So, that means using this you can see that, so this kappa of T alpha T mu which is given by the trace of add T lambda times add T mu. So, since add T lambda all T mu both are semisimple elements on acting on this G. So, these are all the eigenvalues that are given. So, that shows that if you compute this lambda mu, so this is going to be exactly equal to summation alpha of T lambda times alpha of T mu over alpha in phi. Okay, because on H it is 0. So, only on G alpha it will act as alpha of T alpha times alpha of T mu. So, this is the formula we have for all lambda mu inside H star. Okay. So, now if we just restrict this formula to beta, where beta is coming from phi. So, then you can see that then beta comma beta. So, that is going to be equal to summation alpha T beta times alpha again T beta. So, alpha coming from phi. So, now alpha of T beta, so then that will become square. So, note that alpha of T beta is nothing but given by kappa of T beta comma T alpha. So, which is exactly alpha of beta. So, then this beta comma beta is exactly equal to summation alpha comma beta square, where alpha runs over phi. So, now if you just divide by 4 times beta beta square. So, then you get that 4 divided by beta beta is exactly equal to summation twice alpha beta divided by beta beta whole square, where alpha running over phi. Note that these numbers are all integers and these are all non-negative integers. So, in particularly you can see that this beta beta, so that will be actually positive integer. So, this beta beta now you can see that, so this is sorry not positive, it is a positive rational number. So, these are all squares, okay, and this is actually 0 if and only if beta beta is 0, but then you can see that if this is 0 then that will force us that alpha beta is 0 for all alpha in phi. Okay. So, that will force that alpha is actually in the orthogonal complement of H star, but kappa is being non-degenerate. So, that will force that kappa. So, the form that we defined on H star is also non-degenerate. So, that forces that this alpha is 0. So, that is a contradiction because alpha is sorry. So, this is for beta we have to write. So, this is beta, which is a contradiction because to begin with beta we started with in phi. Okay. So, that forces that this product beta beta. So, that must be positive and that is also positive rational number because all these numbers are non-negative integers. So, now if we take lambda from EQ, then again you can see that if lambda if it is comes from EQ, so then the same formula tells us that the product lambda lambda is equal to exactly summation alpha lambda square, where alpha coming from phi. Again, since these are all non-negative squares, and again if this is 0 if and only if alpha lambda is 0 for all alpha. So, this is 0 if and only if alpha lambda is 0 for all alpha in phi. So, that forces that lambda is in the H star perp, but that is already 0, okay, that is a contradiction. So, that tells you that this lambda lambda must be positive if and only if lambda is non-zero. So, that is the definition of positive definite form. So, indeed what we proved that the form that we defined on this EQ, so that must be positive definite. So, this is positive definite. So, now if we take this tensor with R, so then we can extend naturally this form to E. So, where EQ tensor R if we take, so then one can extend the form to capital E. So, then here also we get naturally the positive definite form. So, positive definite symmetric bilinear form. So, now if you have a real vector space with the positive definite bilinear form, so that space will be called Euclidean space. Okay. So, then E becomes actually Euclidean space. So, now because we are came down to actually Euclidean space, so we can use all the information that we have for in terms of this Euclidean geometry. So, indeed we will actually use those information that constraints that we have already on the set of roots, and then bit of this Euclidean geometry to conclude more about the set of roots. So, so far what we have done, we can see that so we started with this H star, and then we observed that this phi is actually spans this H star. So, the span of phi is indeed equal to H star. So, we fix the basis alpha 1 etcetera alpha L inside this phi. So, that is the basis of this H star. So, then what we realized that if you take span of this alpha 1 etcetera alpha L over Q, then that must contain phi. So, that means the span of this Q, span of this alpha 1 etcetera alpha L over Q. So, that must be equal to the span of phi over Q, that is what we observed. And then the form that we defined on H star, if we restrict that to this E Q, then we proved that that form that is defined on this E Q must be positive definite. So, that is what we proved. So, then to go from this Q vector space to R vector space, what we did, we just tensored over, we took this E Q and then tensored over R over Q. So, this is called extending scalars. So, now extending this bilinear form to this capital E, we got actually Euclidean space. So, this way we got actually the Euclidean space that is required. So, now I will summarize what are all the properties of this roots inside this Euclidean space. So, here is a theorem. So, this is very important theorem. So, let G H phi as above. So, that means G is a finite dimensional semi-simple Lie algebra with the maximal toral subalgebra H, and then phi is the set of roots with respect to this pair G comma H. So, then what we have this E that is also defined as above. So, then again, so this E is a Euclidean space. So, what we observed? We observed that this phi is actually a finite subset of this E, and 0 is not in E. So, these properties are there, and the second property, the span of this phi again over reals. So, that is going to be exactly equal to E. The third property, if alpha is in phi, so then minus alpha is also in phi. So, this is something we proved. The fourth property, if alpha is in phi and C alpha is also in phi for some C non-zero. So, now you can take it to be real number, not a problem. So, then what we proved? We proved that C must be plus or minus 1. The fifth property, that if alpha and beta both are in phi, so then you look at this number beta minus beta of H alpha alpha, but beta of H alpha is given by twice beta alpha divided by alpha alpha. So, we write that beta alpha divided by alpha alpha alpha. So, this must be again a root. So, this is very important property. So, now what is more? So, not only this, so if we take again alpha beta inside phi, then these numbers that we were looking at beta of H alpha, which is 2 beta alpha divided by alpha alpha, we observe that. So, they have this integrality property. So, this is very important property called integrality. So, if a finite subset that does not contain 0 satisfies all these conditions, okay, so that will be called actually root system. So, this phi inside E is called root system if it satisfies all those above property, satisfies all the all properties that is in 1 to 6. Okay. So, this is the definition of root system. So, indeed what we have done now, so we have started with this semi-simple Lie algebra and have fixed this maximal toral subalgebra. Then with this respect to this pair, we associated this what is called the set of roots. So, which is of course very much depends upon the choice of maximal toral subalgebra for time being. And so, given this pair G comma H, we have actually associated this phi of h, which is sitting inside this Euclidean space E. So, this is the root system that we have associated. Okay. So, later what we are going to prove, okay, this is look ahead. So, we will prove that so this association is actually independent of the choice of this Cartan's, sorry, the maximal subalgebra. Okay, what is the meaning of that? So, this is the fact, if H and H dash, so both are maximal toral subalgebras, maximal toral subalgebras of G. So, then one can prove that the H and H dash, they are conjugate. So, conjugate means there is an automorphism of G that maps H to H dash. Again, this automorphism can be chosen from inner automorphism. So, they are conjugate under some inner automorphism of G. So, recall what is inner automorphism. So, inner automorphism, it is a subgroup of automorphism. So, it is subgroup of automorphism of G. So, which is actually generated by this exponential of add x, where x is in G such that add x is nilpotent. So, this subgroup is called the subgroup of inner automorphism of G, and we will prove that any two maximal toral subalgebras. So, they must be actually conjugate under some inner automorphism. Now, using this, so once you have this G H and then this G H dash, now you know that G and G H and H dash, they are conjugate. So, then if you look at, so then this will imply, since H and H dash are conjugate. So, using this we will get that this phi of H will be isomorphic to phi of H dash as root systems. Okay. So, that means this association that we did by fixing this maximal toral subalgebra. So, this root system that we associated this phi of H, that becomes independent of the choice of H. So, that is actually a very big result, but anyway, so that is what we will prove. So, that actually tells us that this association that we have made now, it is actually a well defined map from the isomorphism classes of semi simple Lie algebras to the isomorphism classes of root system. So, basically this allows us to define the map from the isomorphism classes of finite dimensional semi simple Lie algebras to the isomorphisms of isomorphism classes of finite root systems. Okay. So, we will never consider the infinite root system, but anyway I am just writing it as finite root system. So, what is the association is given? You take G and then fix Cartan inside G and then send it to the root system associated with this pair G comma H. So, later we will prove that for each root system we will be able to construct one finite dimensional semi simple Lie algebra. So, that this map, okay, which we call it phi var phi, this map is actually surjective. So, again later we will prove that this map is also injective. So, proving this map is injective is not that hard, actually proving this map is surjective is bit hard. Okay. So, indeed this map we will prove that. So, this is the ultimate theorem. Okay, this is the ultimate theorem that this map phi is indeed gives us bijective correspondence between between this isomorphism classes of finite dimensional Lie algebras, isomorphism classes of finite dimensional semi simple Lie algebras, and the isomorphism classes of root systems. So, this way we will actually bring down our problem of classifying finite dimensional semi simple Lie algebras to the classifying this finite root systems. Okay. So, actually we will do all these works later. So, now because we have associated given Lie algebra, given finite dimensional semi simple Lie algebra to this root system. So, we will actually take this abstract properties of root system and then try to understand the root system much more. Okay. Using these properties, we will actually first understand the abstract root systems, and then we will just classify them. So, that will be just a combinatorial ideas. Okay. Not much algebra will be needed there in order to classify this root system. Then after that, later if we get time, we will go back to this Whorf map and then see how one can actually start with the root system and then construct finite dimensional semi simple Lie algebra whose root system will be the root system that we started with, and we will also see why this map is actually injective. Okay. So, this will be the ultimate goal of this course, proving that this phi is actually gives us bijective correspondence, and using this bijective correspondence we will bring down the classification of finite dimensional semi simple Lie algebras to the classification of these finite root systems, and then we will complete the classification of finite root systems. Okay. So, this is our ultimate goal. So, we will actually slowly move into that. So, as I said, so in the next class onwards I will focus on root systems, and then we will actually try to classify all the finite root systems. Okay. I will stop here. Thanks.